Buenos días a todos. Muchísimas gracias por venir a esta oportunidad de nuevo que tenemos en la Universidad de Almería de disfrutar de la presencia de una persona muy relevante en la ciencia internacional. En este caso se trata de Brian Schmidt, Premio Nobel de Física en 2011. Bueno, os contaré muy poquito de los méritos de Brian, porque casi todos los conocéis, y lo que sí quiero remarcar un poco es lo relevante que es para la Universidad de Almería el poder contar con la presencia de personas con un nivel de desarrollo científico tan elevado como el que hoy tenemos con nosotros. Brian Schmidt es de nació en Estados Unidos, luego estudió en la Universidad de Arizona, si no lo recuerdo mal, luego se marchó a Australia, obtuvo la nacionalidad australiana, ha sido 8 años rector de la Universidad Nacional de Australia, con lo cual, si seguimos la costumbre de nuestras universidades, sigue siendo rector, ¿no? Siempre le damos el trato de rector. Y ha desarrollado una amplísima carrera científica. El Premio Nobel lo obtuvo por su descubrimiento sobre la aceleración acelerada, la expansión acelerada del universo, un trabajo que fue fruto de su propia tesis doctoral. Es decir, los trabajos que dieron lugar al conseguir el Premio Nobel se obtuvieron a raíz de las primeras investigaciones que hizo con su propia tesis doctoral, lo cual ya es un índice de la precocidad científica de Brian. Es cierto que el descubrimiento fue simultáneo con otro grupo de investigación norteamericano, con lo cual el Premio Nobel fue compartido, pero evidentemente eso lo que nos lleva es a la grandiosidad de la ciencia. El conocimiento humano compartido, el conocimiento que avanza mucho más de lo que podemos imaginar, es lo que nos mueve en el día a día a las personas que intentamos hacer ciencia para ser cada vez un apoyo más grande a nuestra sociedad. Yo no quiero extenderme mucho. A mi derecha tenemos todos lo conocéis, pero lo presentaré también, a John Beckman, doctor honoris causa por la Universidad de Almería. Es mi ahijado, con lo cual le tengo mucho cariño. Y bueno, de John puedo hablar muchísimo, no quiero extenderme en esta presentación. John también es una figura de primer nivel en astrofísica y astronomía. Él hará de traductor en el turno de preguntas. Después de la charla de Brian habrá un turno de preguntas y respuestas, y John nos ayudará con la traducción si es que hace falta algún tipo de traducción en la pregunta. Bien, no quiero extender mucho más. Brian, welcome to the University of Almería. We are very happy to have you here with us. It's an honor for us to count on you for this talk. And now, Brian, the floor is yours. Thank you.
So hello everyone. So today I will be giving what I would describe as a physics colloquium. So yesterday I gave a public talk. This will be meant to be people, you don't have to be an expert in cosmology, but it sort of assumes a certain level of understanding of physics, and so hopefully that will be okay for most of you. There will be something in here if you're not up to speed on physics, and hopefully we'll keep everyone in the same place. So it's been a great but short visit here to Almería. It's the first time I've been down here, and it is lovely to see such a vibrant campus. It reminds me a lot of the University of Arizona campus where I was an undergraduate. So let's just get started. And cosmology, to my mind, started when this person, who most of you will not know, Vesto Melvin Slipher, went through and started looking at the spectra of galaxies. Now, we did not know what galaxies were during this time. They were fuzzy blobs. They were called nebulae. And what he saw by stretching out or by measuring the spectra with photographic plates is he saw the spectral lines of the sun stretched redward in almost every one of these nebulae. Now, we knew about the Doppler shift, and it was interpreted as the Doppler shift, and that speed of the motion was typically hundreds to thousands of kilometers per second. But the fact that they were all in the same direction, well, that was a real mystery, because it would indicate everything was moving away from us. And given the idea of Copernicus that our part of the universe should be the same as every other part of the universe, it seemed hard to imagine that everything should be moving away from us without us being a special place. So that was a mystery. And the mystery was worked on by measuring distances. And so Edwin Hubble in 1929 had started measuring distances by looking at how bright the brightest star was in these nebulae. At this point, we had realized, due to Hubble, that the nebulae were a long ways away, and they were galaxies. That the Milky Way was a galaxy, and that these were little galaxies, not unlike the Milky Way that we were part of. So that evolution of understanding had occurred in these 10 years. And so Hubble measured the brightest star he could measure. He compared it how bright it was to other galaxies' brightest stars, and then relative distances between the galaxies were constructed from effectively a benchmark, for example, the Andromeda galaxy, and outwards. And so when he did that, using the inverse square law, when he did that, he published this diagram in 1929. And this diagram is very consequential, because it showed, indeed, that the further an object was away, the faster it was moving away from us. And it is from this that the idea that the universe was expanding was truly demonstrated. Now, a few complications. First of all, it turns out that with the telescopes of the day, when Hubble looked at a galaxy that was quite a ways away, the biggest stars actually were in clusters, and you didn't just see one star, you saw many stars. So it turns out he got the right answer, but it was the actual comparison of distance velocity was off by almost a factor, not quite of 10, but a factor of 7 or 8. Very poor. The other thing is another astronomer, Lamat, who was in Belgium, more or less did this same work in 1926, 1927, during his PhD thesis. He showed Einstein his work, and Einstein dismissed it as being, he said at the time, your mathematics is fine, your physics is abominable, and kind of walked off. So Hubble discovered the expansion of the universe, but really Lamat did it as well. So the universe is expanding, and you can think of this in your head just as an explosion. The further away the shrapnel is away from you, then that's sort of from a time. But it turns out if everything is expanding, everyone sees exactly the same thing. Now, to tie this together from a theoretical point of view, we have Einstein. And in 1907, Einstein had what he described as his greatest thought. The idea that acceleration and gravitation are intricately linked. They are equivalent in any way, shape that you think about them. And that requirement, that acceleration and that gravitation are interchangeable, they are equivalent, was seemingly simple, but to make it all work, along with his understanding of special relativity done in 1905, he had to develop the equations of general relativity. Now, while he was working on this, he had to learn a whole bunch of mathematics that he was unfamiliar with. That was right at the cutting edge of mathematics of the day. He worked with Hilbert. Max Planck, the very famous physicist, told him, "What you're working on is too hard and you will never understand it, and if you do, no one will ever believe you." So, encouraging works from Max Planck. But he persisted, and in 1915, in November, he published his equations of general relativity, which are the basis of our understanding of gravitation today. They have never shown to be wrong, and they have indeed predicted many, many phenomena since 1915 that has always been shown to be correct as accurately as we can measure. So those equations predicted curved space, which was tested out in an eclipse where you could measure the position of stars. This was done by Alfred Eddington, 1919, published with great fanfare. And the equations of general relativity allowed Einstein and others to start looking at what the universe, how the universe would behave, because Newtonian physics really doesn't work in a universe without end. It effectively has no solution except for the universe being empty. And so Einstein very soon realized that his equations of general relativity made the universe dynamic. This is 1916. We don't know the universe is expanding. We look out, Einstein looks out, sees a static universe. He then realizes his equations of general relativity are missing something that can be in there. An addition, sort of, but one that is the moral equivalent of an integration constant when you solve a mathematical problem. And this constant, the cosmological constant, we think of now as the energy that space has. So what is space empty? If it has a cosmological constant, space is not empty. It has an energy associated with it per cubic meter, and you need to worry about that because it affects the dynamics. Indeed, it causes gravity. The gravitation of dark energy is repulsive from itself. And so Einstein's idea would be that you would tune up the amount of cosmological constant in the universe to equal the force of gravity and make the universe static. Now it turns out it's unstable, and so it was not a solution. And later on in life, because he persisted with this for many, many years, later on in life, he retracted that idea, called himself a donkey for sticking along with it for so many years. So our paradigm for understanding the universe is based on general relativity, the theory, and some assumptions. And those assumptions are that the universe is homogeneous and isotropic. So that means it's not rotating, it has no preferred direction, and it means that every part of the universe, at least on large scales, is the same as every other part of the universe. Now clearly, we're not homogeneous in this room, but this is not a large part of the universe. But imagine I take a box of the universe that is 1 billion light years by 1 billion light years by 1 billion light years, and I measure its density, its temperature, all of its parameters, its chemical makeup. This assumes that if I do that, all those boxes will be the same in the universe at a given time. And as near as we can tell later on in life, that is true, but the reason they did this this approximation, starting in 1923 with Alexander Friedmann. It turns out that Lamont also did this independently a few years later. You did it because it allows you to take general relativity and make it a solvable set of equations. All right? So the standard model, and I'm going to show you the equations. You don't really need to understand what's going here, but I think it's good just to see how it works. So if you go through and take the field equations, which are through a tensor formalism, a large number, like 20 coupled nonlinear equations, when you make the universe isotropic and homogeneous, you could break it down into two ordinary differential equations, the one of which I care about is this one. And that is actually quite a simple equation. So you've got 1 over c squared, c being the speed of light, dA. A is a very important concept we're going to refer to. It is called the scale factor of the universe. So A talks about the relative size of a piece of universe over time. Normally, if the universe has curvature, which it might, or it has even if it doesn't have curvature, it always has an epsilon of curvature. It's the radius of curvature of the universe. That's what you can think of it as. So that scale factor, turns out, tracks the size of a piece of the universe. And conveniently, what Slipher saw as that motion away from us was not the Doppler shift. It was actually the scale factor of the universe changing. And we call essentially 1 over that plus 1 the redshift. So the redshift is how much a galaxy's light is moved relative to the rest wavelength. And it turns out, because as light travels through space, as space stretches, the light's wavelength stretches with the expansion of space. And it turns out you can measure the scale factor change of the universe to about 5 decimal places, very trivially. So we can measure to a part in 100,000 very accurately. Some of you will have seen Michel Mayor. That same technology to look for exoplanets is essentially what we use here. So it is tracked by the redshift, how much light is stretched. That tells you how A changes over time. Okay? So the other thing we need to worry about in this equation, is rho. That's the density of material. Now, it's a little tricky because the density evolves, and so rho will be a fraction of A. And then finally you have K. K is the curvature, and the curvature can be 0 if the universe is flat, or plus or minus 1. And so if you have a flat universe, then it turns out that triangles geometry is simply given as you would expect in Euclidean space. But relativity allows the universe to have geometries of being hyperbolic, that's a k equal minus 1, or spherical, k equals plus 1. And in this case, the way you get from point A to point B in the universe is more complex. You don't just get to go on a straight line, you have to follow what we call a geodesic. And because space is curved, like on Earth, when I go to Canberra from here, I don't get to tunnel through the Earth on a straight line to Canberra. I have to follow the surface. That turns out to go over Iran right now, so I can't even do that. So I have to deviate from the straight line, but you got the basic idea. So in the same way we're comfortable with traveling on geodesics on planet Earth, the universe is the same. It's just very non-intuitive because the curvature of space is related to time. I'm not going to go into the details here. Go to a little bit here in a little bit. And you have some complex accounting, which I'll show you. All right. So you can go through and solve that, and this is a problem we would typically do in third-year astrophysics, is you solve that differential equation. And these are the solutions for k equals -1, k equals 0, and k equals +1. Let's do the simple one, the flat universe. You literally get that the scale factor relative to what it is now, A0 is the radius of curvature of the universe now, or the scale of the universe now. Scale says time to the 2/3. The universe stretches at t to the 2/3, so it's effectively kind of slows down over time, and effectively at t equal infinity, it's kind of come to an end. All right, if you've got the other two, you've got some fancy trigonometric terms, and you end up, it turns out, in the case of the cosine terms, you get cyclic universes. Now, in astronomy, we use some parameters that are true to astronomy, but we use them so much, I need to tell you about them. We have the Hubble parameter. We often call the Hubble parameter the Hubble constant, but which is the rate the universe is expanding right now. But the rate changes over time, and so it is the derivative, the time derivative of the scale factor divided by the scale factor. So it's essentially the fractional change of the scale factor over time. Turns out we've measured this. I measured this for my PhD thesis, and right now we use in astronomers' units that the Hubble constant is roughly 70 kilometers per second per megaparsec. That means that a galaxy that is a megaparsec away, and a megaparsec is 3.08 million light years, another astronomy term, but if I put it into sensible units, I will in a second, it's 1 over time, it turns out. So if you're 1 megaparsec away, you're moving 70 kilometers per second on average, or that's what your redshift will be in terms of a velocity equivalent to the stretching of the light. So you'll see you have kilometers and megaparsecs, they're both distances. So it turns out the natural for the Hubble constant is 1 over time, where that is the characteristic age of the universe, right? That essentially tells you if the universe starts at a point, the Big Bang, that's how long it takes to get to its current scale. And that's about 14 billion years, which may remind you very much of the age of the universe, because that's more or less how we figure it out. Now, there is a critical density. The critical density you can write down in these equations when you solve that differential equation. 3 times the Hubble constant squared divided by 8 pi, the gravitational constant. That is the critical place where the universe becomes dense enough that its geometry goes from being flat to closed, where it comes onto itself. Okay? If you're below that critical density, the universe has hyperbolic geometry. If you're heavier than the critical density, you have closed spherical geometry. So that is a very important number. And of course, you cannot exactly be the critical density, but you can be very, very close to it, it turns out. So you put the numbers in, and the critical density is 9.2 times 10 to the minus 27 kilograms per meter cubed. So the density of Earth, 5,500 kilograms per meter cubed. This is 30 orders of magnitude less. So that tells you one of two things. Either we're very, very much heavier than the critical density, the universe is, or we live in a very unusual part of the universe. And it turns out the Earth is a very, very unusual part of the universe. Most of the universe is empty. And it turns out places like the Earth represent about 1 part in 10 to the 30 of the universe. And as we'll see, the universe is effectively at the critical density to as accurately as we can measure it, and we can measure it pretty accurately. So the density parameter is the density that's in the universe divided by this critical density, and it turns out, because the Hubble constant changes over time, h changes, the critical density changes over time as well. As the universe evolves, the critical density evolves with the universe. All right, so if we look at these equations, let's forget about the numbers and let's see what they look like on a piece of paper. So imagine you have a universe that has no density whatsoever. Okay, it is absolutely stone cold empty. Then it's very easy to do that. It's a straight line. Okay? Now, if the universe is hyperbolic, that is, k is -1, but there is some density in it, then the universe has that structure, and you'll see some coshes, so hyperbolic cosines and things in it. If the universe moves to being into the cosine solution, because k is +1, then it has this nice, very symmetric, it gets bigger and then gets smaller. So all these universes start with the Big Bang, but only the heavy ones end with the Ganab did, the Big Bang, backwards. Okay. Now, one other little thing, and then we're going to be done. Well, we're going to get through most of the equations here. We're almost done. So, when we solve those equations, I put rho. Now, we know that rho goes as the scale factor to the -3. That is, if I put an atom in a box, and I make the box twice as big, the volume in the box goes up by a factor of 8, the density drops by a factor of 8. But the universe can have things other than atoms in it. Okay? So, imagine the universe has a photon in it. Then that photon does not go like normal matter. The photon gets stretched by the box, and its wavelength gets lengthened. Its energy, E equals h nu, drops. And so its density actually goes as the 4th power of the scale factor, not the 3rd. When I put that into my equations, those differential equations, it affects the way the universe expands. The cosmological constant, which we're going to come back to, Einstein's idea, is the magical thing that is part of space itself. So it is invariant as the universe expands. Its density stays the same. It has, therefore, a different equation of state, a different way it reacts to the universe's expansion. And when you go through, and I'll just skip this for now, and try to use this equation then to solve this, and it turns out you can do some substitutions. That's what the equation looks like. And if you just solve it, the important thing here, I'm just going to go up and show you, is I have to go through and make a substitution on the second line. And I'm not going to show you here. But you substitute out, you have to put the equation of state in there. And that gives you this t to the 2/3 solution for atoms, if the universe is made up of atoms. If you instead put photons in there, it's a different substitution. Then the universe expands. It turns out it slows down much faster. It goes as t to the 1/2. So it has a different expansion. If you have a cosmological constant and you put that in, then you get exponential growth. It's not slowing down. It's speeding up. It's accelerating. Okay? So what's in the universe gives you different solutions. Okay. So that was a long way to go to get that basic concept, but you're physicists, and I know you guys are always upset when I don't actually show it to you. For those of you who aren't physicists, you probably thought I could have gotten on with it for the last 15 minutes. All right. So what you end up in our universe is when we look out at the universe right now, to cut a long story short, we know the universe has photons in it. We know the universe has matter in it. And as I will show you, we think the universe has a cosmological constant in it. Now let's think how this works. Right now, the universe seems, as I'll show you, to be exponentially expanding. The cosmological constant, therefore, makes the universe get bigger and bigger. Its density is constant. Therefore, nothing's going to slow it down. It just keeps going. So once the cosmological constant starts exponentially expanding the universe, unless for some reason it disappears, it just keeps going, and the universe exponentially expands. But if we look back in time, when the universe was smaller, our density goes up. The cosmological constant stays flat. So if the universe has atoms and a cosmological constant, at some point in the past, there will be more density of us than the cosmological constant. And during that time, the universe will actually expand at t to the 2/3 rather than this exponential growth. Therefore, we know at some point there must have been a transition from exponential expansion in the past to something that looks like the t to the 2/3 solution. We also know the universe has photons in it. Photons' density goes up as the 4th power of the redshift. So if I have atoms and photons, as I go back in time, there will be a time in the past where the density of photons will exceed the density of atoms. Okay? There will be a time when photons rule gravity. And so you naturally get these phases where the universe expands with photons, t to the 1/2, matter, t to the 2/3, and if there is a cosmological constant, you get exponential expansion. That's what those equations say in sum. Okay? All right. Now, the final thing. I told you we live in a universe that's complicated. Okay? We have to get from point A to point B. And that universe is not only potentially curved, it's also expanding. And so we have what we call a metric, the Robertson-Walker line metric, which looks like this. It's actually not that complicated, but it includes this evolution of the universe, geometry, and curvature. And so if I want to get from point A to point B, that's the geodesic, I have to worry about time. I have to worry about my coordinates in the universe. Like, that's just latitude and longitude if you think about it on Earth. I got to worry about curvature, and I got to worry about the dynamics that comes from solving that differential equation. So it's actually non-trivial to figure out how light travels, but that equation tells you how to keep track of everything. Okay? And so it effectively allows you to go through and figure out in these different universes how light moves from point A to point B over time. Okay? So you put this all together. You want to measure the distance to something. How bright does a star look back in time, for example? Then you put this all together and voila, someone much smarter than me a long time ago gave you the equation. That's what it looks like. I'm not going to give you any insights there, except for effectively how far an object is away it appears in the universe depends exclusively on what is in the universe. That is essentially given by the omegas here. That's how much of each, how many photons there are, how many atoms there are, how much cosmological constants, and their equation of state, which is given by W, which essentially tells you how it reacts to an expanding universe. Okay? You've got geometry, and then I can figure out how far away an object will be as a function of redshift, and that's what we can compare to. Okay, so what it looks like on paper, again, the equations, is that depending on what the universe looks like, as I measure distance compared to redshift, the universe is going to have different relations. And I can figure out what the universe is made of by measuring distance and redshift back in time. Now there's a couple little things that, for your amusement, it's worthwhile understanding. I'm someone who likes to look at exploding stars. Stars have a certain brightness, so I measure how bright those stars are back in time to get the distance, and I use the inverse square law. And you can see that this is a logarithmic over there on the left. That's a logarithmic diagram, and as you go further and further away, they spread out into different answers. Here I have gone through and I've subtracted off essentially the base case. That's an empty universe. And you can see that objects that have, for example, a bit of atoms, that's omega matter, they essentially, at a given redshift, are brighter than an empty universe. But objects that are really dense are even brighter still. And that's because the universe is slowing down back in time. A universe that, for example, has a cosmological constant that's accelerating, that universe turns out to be fainter most of the time until we get to a time when matter, because of the diminution of the expansion of the universe, causes us to become more dominant than the cosmological constant. And so we get this curve that's brighter, and then it kind of tracks, it turns out, the matter one. And that's because this curve here, the cosmological constant is no longer important. It's only matter, and indeed it's exactly the same set of equations when you get to a large redshift between those two. So that's how we can measure, is I just have to measure distances and put it on this curve, and I can say, am I on this trajectory, or this trajectory, and that allows me to measure what's going on in the universe. If I were to measure rulers, how big something appears in angular size, you get a very unintuitive result when you first think about it. When I look a long, long ways away, the ruler gets smaller and smaller and smaller, but then at a redshift of 2, that's where light is pushed over by a factor of 2 to the red, it doesn't get smaller, it starts getting bigger again. That is, when I look very, very distant in the universe, because the light, as it's traveling to me, the universe is expanding, those light, as I'm looking back, the universe is smaller and smaller, and it focuses the light, and I actually get to magnify things in the distant past of the universe because of this effect. All right, so when I was a kid, John was a mid-career astronomer. This is the world we lived in. We had come up with this idea that to sort of make sense of the universe, theorists thought there must be a time where right after the Big Bang, the universe exponentially expanded many, many, many times, and that was a way to create a flat universe. It turns out when you exponentially expand, you flatten out all the bumps in the universe and you change the geometry. You drive it to essentially a flat universe, okay? It turns out this process, very conveniently, takes quantum fluctuations and grows them by 60 orders of magnitude. And so quantum fluctuations right after the Big Bang become the seeds of the galaxies and everything we see in the universe today. Now, when I was taught this as an undergraduate, I was like, this is crazy. This is like science fiction. Why would you believe it? But the theorists were very keen on it. And then the other thing we needed was something called cold dark matter. Everywhere we looked at, we saw that there was gravity, but there were not atoms associated with that. And turns out, to make a lot of things work, we needed a universe where most of the matter in the universe was not atoms. it was something that was cold, that means there was no thermal velocity, and it did not interact with itself or anything else. It just essentially interacted only by gravity. And it turns out if you put those things together and you looked at how galaxies were spread across the sky, you could more or less predict what you see. All right? The problem is that it predicts a couple things. Flatness, that the universe should be flat. And at the time, that meant that omega matter, that is omega gravity, should be 1. Okay? And it also predicts how galaxy structures grow over time. Now, in 1990, this diagram was made where they went out and they tried to measure the how gravity affected galaxies. And essentially, they made a diagnostic of basically how galaxies were spread across the sky. And there was a problem, which is that that model I just showed you gave the solid line curve, and the dots gave the data from this basically map of 10 million galaxies, and they essentially just said, how likely is it for two galaxies to be next to each other? It's a pairwise measurement. So they showed that a cosmological constant, an accelerating universe, would fix this. And so you might ask, why did they not get credit for measuring or finding an accelerating universe? And that's ultimately because the next year they wrote this paper, several of the same authors, and basically said, we don't really understand how galaxies are made, which was true, and therefore we were probably a little hasty, trying to give up cold dark matter, and we should stick with it. So that brings us to the other way we could mess around with it. We could really play around with the value of the Hubble constant and push it down to values which are much, much lower than any of us thought. I was doing my PhD during this time. I had measured a Hubble constant of 73, and no one thought the Hubble constant could be this low. I will say I made a bet with several of these people about this, said put your money where your mouth is, and they never paid up because Jim Peebles said we weren't sure enough that they were wrong, which I still dispute to this day. All right, so in 1994 there was basically two camps about what was going on. The theorist camp basically said inflation and cold dark matter are correct, omega's 1, the Hubble constant's low, and observers like me just simply got it wrong. We messed up the Hubble constant, we messed up how much matter there is in the universe. Observers said, the theorists are wrong, they're just making stuff up. Who believes this inflation thing anyway? Omega matter is 0.2, the Hubble constant's kind of up above 50, and it's just fine. Inflation and making up things was wrong. But their chance was to go out and do a new experiment. And so here I am showing my value of the Hubble constant in 1993. And the chance we had when I finished my PhD was to go through and actually see what the whole universe was doing and see which of these curves it was on. And to be clear, what we were expecting was camp 1, the theorists, this is the line they're predicting. Camp 2, the observers, this is the line they're predicting. And we could just separate those things out. Easy. 3 years of hard work if we have the right tools. And it turns out the tools that my colleagues in Chile had developed, type 1a supernovae, were able to measure distances to large redshifts because of their work. They had developed the tools to effectively build on the work of Fritz Zwicky, who first did this, and to effectively use how long it takes for a supernova to rise and fall to calibrate its luminosity, its intrinsic energy. And it turns out they could calibrate it to about 7%. Now, 7% was 4 times better than any other method at the time. And these were the brightest things around. They're 5 billion times brighter than the sun. They're brighter than an entire galaxy. And so we could see them, it turns out, with the modern telescopes and the new digital detectors that were being put on them, CCDs, out to redshifts beyond 0.5 with 4-meter telescopes. And with the 10-meter Keck telescope, we could actually get a spectrum of it to measure its redshift. So my friends in Chile here did this work. They had to do it without digital detectors because they weren't around big enough. They used photographic detectors to find them, and then they did their measurements with digital detectors. And they discovered that these type 1a supernovae were not all the same, but they could be calibrated, as I told you. And Mark Phillips, amongst them, showed this relationship that the slower a supernova was, the brighter it was, and that relationship was calibratable to 7%. So in 1994, Mario Hamwi from this group came and showed me this diagram. It's measuring distance versus redshift, and you can see all those dots lie right on the line. And he used an independent calibration, so he didn't have an extra degree of freedom. And when I saw that, I said, I'm stopping what I'm doing. This is the future. Because no one had ever seen a Hubble diagram, which is what this is called, distance versus redshift, that looked anything like that. Normally, they look like a scatter diagram with some correlation. Okay? So, eventually these guys found 29 supernovae, and they were used by both teams, it turns out, to measure the acceleration. Saul Perlmutter, turns out, was using digital detectors at Berkeley to look for type 1a supernovae. And for 5 years, he had been very quiet and not really found anything. In 1994, just after Mario visited, he called us up and said, we have an object for you to look at. We looked at it, and we saw that it was a redshift 0.425, so its light was stretched by 42.5%, and it was clearly a type 1 supernova. So that demonstrated you could actually discover these things with the new technology. We tried to work with Saul about how we might do it. I would just say he's from a physics background, we're from an astronomy background, and it was clear we were going to have irreconcilable differences about how to do this experiment. That's a nice way to say it. And we agreed that we would do it our way, he would do it their way, and hence started with Nick Sunsef and me. I was about to move to Australia, building up a team of supernova experts to go through and do this experiment I was telling about. Saul and his team, with his physics lab, was doing it their way. So the challenge that Saul had been working on for 5 years is with these digital detectors, and here's one of them. So this is a 2K by 4K CCD image. So that's 8 megapixels. There would be 8 of these taken on the telescope at a time, and we would take 150 images a night. So it turns out we had to get through 50 gigabytes of data. Now, type 1a supernovae are rare. The last one that occurred in the Milky Way was observed by Kepler and Galileo in 1604. So they only happen every several hundred years in a galaxy. So if I want to find, for example, 3, I have to take all of this data and process it and find what has changed. And by finding what has changed, not so bad now with modern computers, but at the time it was very challenging. The computers were slow, and we had disk drives that only held a gigabyte of data, yet we took 50 gigabytes of data in a night. So my solution as a young postdoc was to write software that would, with a spaghetti ball of Perl, if you remember Perl, would go out and run on every computer at the observatories in Chile and essentially try to match these images up with images we had taken a month earlier, convolve them so they looked identical, scale them, and then subtract them, and then find the differences. Now that turns out to have been quite challenging at the time. There's a reason it took Sol 5 years. But effectively you need to find, in 1,500 images like that, 3 of these. And that image, pretty easy to see that nothing has come to something there in those 3 weeks. But there's so much data, you have to automate it, okay? That object turned out to be at a redshift of 0.5, which means it was 5 billion light years in the past. It exploded before Earth was formed. That's the beauty of this experiment. You literally get to look back in time. So, I take you to Chile just to show you what this was like. In one of our runs back then, that's Greg Aldery from the other team, from Sol Perlmutter's team, because they used to get a night, we used to get a night. They got a night, we got a night. And Nick Sunsef here. And so we get 6 nights a year on this telescope, which is more telescope time than anyone else on the planet. And there's a very young me and Nick Sunsef at the control. We've got to make sure everything's fine, because you only get 6 chances a year, right? And so the data is going through, it's running through my software. My software, to be honest, is not very good. So we have a sweatshop of astronomers going in and saying, yeah, no, that's just junk, that's junk. And we have to work fast. So at the end, we put it all together, because we have to, a day later, send everything to Hawaii to the Keck telescope, which has been scheduled directly after this. And here at the largest telescope on the planet are 2 team members, Alex Filippenko and Adam Rees, who are taking our finding charts and looking at them. And of course, there's 2 Keck telescopes, and at the other Keck telescope, Sol Perlmutter is working because he has time on that telescope at the same time. So we worked very competitively, but kind of in synchronicity, and the work did start showing things. Our first object very interestingly showed a spread of curves which indicated the universe might be accelerating. We just figured it was a bad measurement. But then when we got through everything, and I'm going to skip this part right now. It's all right. I will go through and move us to the actual discovery. We do this for 3 years, and in 1997, Adam Rees, here's his own lab book, goes through and with a sample of 12 objects sees that that first object we saw was not a fluke, that it seemed to indicate that when we did an omega matter measurement, the amount of mass in the universe was negative, which didn't really make sense, and so we had to go through and add an extra parameter, the cosmological constant, to make it work. Now, I'll be honest, when he sent me the first figure of this, I called him up and I said, Adam, what did you do wrong? We spent many months going through each part of the analysis. Eventually, I was convinced he hadn't made any major mistakes. Like anything, there were some little minor ones along the way. We then had to go, Adam and I, to the rest of the team and say, all right, guys. And they said, what did you guys do wrong? And we did the whole process again. But in the end, in February, well, this is in January, this is what the team, who had quite different reactions to this. Alex Filippenko just awarded the Gruber Prize this last week. Basically says, who knows, this might be the right answer. He's very excited. Bruno Leibengut, my Swiss colleague, basically very skeptical. There's no point writing an article if we're not absolutely sure. Bob Kirshner, who was my PhD supervisor at Adam Rees's, I'm worried. In your heart, you know the cosmological constant is wrong. Though your head tells you that you don't care, you're just reporting the observations. So he's very concerned about this being wrong, intelligently. Mark Phillips, who's the inventor of the method we use as serious and responsible scientists, we all know it's far too early to reach firm conclusions. So he's not convinced yet. John Tonry makes more of a physicist, thinks we should get going. And Alejandro Clacchiati in Chile doesn't mind making mistakes. Nick Sunseth, the co-founder of the team, says this is really important, work on it, let's see what we get. And I think that was the absolute right thing to think about as we did this. In the end, after a couple months, everyone was convinced. We were uncomfortable, and we were worried not about us making a mistake on what we knew. We were worried about Donald Rumsfeld's unknown unknowns, the things we don't even know about yet. And at some point, as a scientist, you can't be worried about that because that's not your job. If you're wrong, for that reason, you progress the field because you learned something new. So here's what the data looked like. Both teams, it turns out, got the same answer at the same time. And each result was about 3.5 sigma on its own, combined 4.5 sigma. The universe seems to be accelerating, and if you put it in a probability diagram, you get that with about 99.995% probability, the universe seems to be speeding up over time. So that is the results from that time. And it is for that that the two teams were awarded the Nobel Prize. And I will say, winning a Nobel Prize is quite an event. The Swedes treat you incredibly well. But it is very disrupting for one's life. Now, lots of questions emerge. Why is the universe just now starting to accelerate? Remember I told you that it's inevitable, it's going to happen at some point. But happening just at the time you are here as humanity, that always raises a little bit of an alarm bell. We still don't know the answer. Seems to be just the way it is. There are anthropic reasons, saying if it were any earlier, then the Earth would not have been able to form, we would not be able to be observing it, and, well, maybe true, perhaps not very satisfactory as a physicist. So, I think we've talked a bit about that already. So the first thing one needs to do is to come up with another way to measure this. And the cosmic microwave background, you're actually looking at sound waves that have been propagated by what we think are these quantum fluctuations that were expanded. And it turns out we can use these to measure the physics of the early universe, because the wave action of the universe, of essentially fluctuations in the universe, depends on what the universe is made. By this diagram, if you've got cold dark matter, or you have atoms, or you have photons, they all interact differently. You can go through and run the acoustic physics, see what the universe looks like, and then look what it looks like in reality. And the cosmic microwave backgrounds, John did some of the earliest experiments in this work, and the theory makes very clear predictions of what the number of different acoustic modes should look like as a function of scale. So large scale on that side, moving to very small scales on this side, you get these very, very complex set of curves. The theory is very, it's challenging but clean. There's no reason it should not be right to very high precision. And so the first thing you can do is you can just measure how big the bumps are. Okay? That turns out depends, remember when I show you the angular size, how big are those acoustic modes look like on the sky? Well, if the universe has different geometries, then you get different answers. And it turns out, emphatically, you can make a measurement on the curvature of the universe. And it turns out that in 1998, you couldn't do it very easily. John, you probably have a few measurements there. But in 2000, it became very clear that we could see the largest bump of acoustic modes, and that told you that the universe was flat to a few percent accuracy. We knew omega total was equal to 1 plus or minus a little bit. Okay? And so in this diagram, that effectively put a new constraint, and it moved our results from being 4 standard deviations, 4.5, to about 8 standard deviations away from a universe that did not have a cosmological constant. This turns out the time when I was confident that we were probably more or less right. But before this experiment, I was not sure, to be honest. Other people went out and looked at the distribution of galaxies, this time not by just taking photographic plates, but taking redshifts of hundreds of thousands of galaxies. This was done in Australia by UK and Australian astronomers. This is what it looks like. And it turns out that different models of the universe basically give you different things. And you can ask yourself, which of the models, 1, 2, 3, 4, looks like the observed? Your eye's pretty good at doing that, and it turns out that's the model. It tells you omega matter is 0.3, but it's invisible. It cannot see the cosmological constant. It can only measure how much matter there is. So on this diagram, you get, that's the galaxy constraint. Turns out that is the cosmic microwave background constraint that's gotten even better. You put it all together, and voila, you get this magic number in the middle where 70% of the universe is a cosmological constant, 30% are atoms and dark matter, and the cosmic microwave background tells you very accurately that 25% of the matter in the universe is dark matter. 25% of the universe is dark matter, 5% are atoms. And we get that from the cosmic bouncing. So what's dark energy? Well, it could be Einstein's cosmological constant. It makes a very strong prediction that it does not change over time. And so you can test it. It turns out it's the easiest thing to test. It's been around since 1915 or 1916. But it's not the only ideas. Another possibility is dark energy changes over time. Here, the theorists kind of get to make up and do anything they want. So very dangerous. And so the way we're going to test this would be, quite frankly, to see that Einstein's version doesn't work, and we need to have something with an extra degree of freedom. So these things are often described as quintessence, which if you go to Japan, you might get your hair done at this place specializing in this. And then finally, maybe Einstein's wrong. Maybe gravitational theory is wrong. And so you'll hear about people talking about Mond and all sorts of stuff. This is a very big bar because the degrees of freedom you have here are basically infinite. And so testing any of these ideas is really, really hard. We can test general relativity. So the main thing to do is to show that general relativity is somehow wrong. And so turning Einstein on his head would be big indeed. So there are many ideas. There are roughly 5,000 theoretical ideas now on the archive. Each idea is a little different than every other idea. My guess is every single one of them is wrong, but maybe one of them's right. We keep on trying to test. So the cosmic microwave background has provided this is the acoustic signature, and it provides an incredibly strong way, as I indicated, of measuring things. And we have now the baryon acoustic oscillations, where those sound waves are imprinted in galaxies. And so we can actually use the sound waves not just from the cosmic microwave background, but see how the sound waves get stretched and pulled by the universe. And this is the data set just released as part of the DESI experiment in the United States. And every dot on here is a real galaxy observed. This is not a simulation. It's actually a data set you're flying through. And you can see that foam-like structure. That turns out is encoding the acoustic signal from the cosmic microwave background, and you can see with very high precision what does it look like and how does it evolve over time. Specifically, what's the size of the acoustic scale, because they get stretched with the universe. Do they go through and do what the cosmological constant plus normal matter universe says, or do we need something that's a little different? So these have become a big thing over time. This is the most recent measurement, and what you can see is the black line is a cosmological constant model, and the dotted line is the best fitting model, and you can see back in the not too distant universe, right here, the dots are just a little below the line. That is the claim for evolving dark energy. Now, it looks interesting, but I'm personally not prepared to say yes or no. They're getting about double the amount of data, so you'll be able to look at it in two halves of the data, and I think you'll get a much better idea. You put it all together, you can measure things like the equation of state, and it turns out when you put everything we have right now, you get actually that the equation of state is -1. That turns out to be the equation of state of the cosmological constant. Kind of hard to argue with that. Everything more or less fits. It's only if you go through and have a peculiar model of evolving dark energy that you start to see things that look a little different. So the supernovae that we did, that's what state-of-the-art looks like right now. It's still really hard to get objects in this area because you kind of have to look at the entire sky with a big telescope. Vera Rubin is that telescope. It will fill that in. And you'll also see the points here lie above the line. Turns out that's exactly the same way as the points in the other experiment, even though it's flipped compared to how I've shown you. So let's stay tuned and see what's going on. I certainly don't believe this yet, but maybe there's a hint that the universe is evolving not quite like the cosmological constant. All right, so I've showed you that. So the universe more or less still looks like this. And as I said, if you choose your evolving dark energy, you can end up off the canonical point. But let's see what happens. It's something as a placeholder to see. The final thing I want to talk about is the Hubble constant tension. When we measure the model of Planck, which is the cosmic microwave background, you naturally get a Hubble constant or a Hubble parameter at the time of the CMB, and it's measured, everything's measured so accurately, I can then bring that Hubble constant to right now. And that number we get right now is that the universe has a Hubble constant of 67.5 kilometers per second megaparsec. We just measure it from Earth out to the nearest galaxies and beyond. We pretty definitively get a number of 73.5. They're off by about 8%. And that's getting close to 5 standard deviations. I think it's more like 4. But, recent work done last year, it looks very, very substantial. Here's the nearby measures, here's the cosmic microwave background measure, and they really, really don't agree. So I think this is the biggest crisis in cosmology, because in cosmology you either get it right or you don't. And at this point, 8% is looking to me to be interesting. What's going on here? I have not seen a single theory paper that seems to give a sensible explanation for this yet. So this could be very, very interesting. I'm working on a different way of measuring here that I think could be very, very good. That'll take 3 years, so I'll see if I agree, but maybe someone will have a brilliant idea. And it turns out I'm using this method down here. The one that's completely independent of the rest of them. That's why I want to do it that way. But any way you look at it, the universe seems to be accelerating. I don't think that's going away. You can do things where you just forget general relativity and just use geometry. That work for a long time has shown that the universe is accelerating with almost nothing other than the universe being homogeneous and isotropic. So I don't see there being any easy way out unless there is some weird thing that the growth of structure does that messes up the Robertson-Walker metric, basically. This is very controversial. Numerical GR calculations now have been done that seem to indicate it's not important. But a few people who are very smart still think this is something we need to worry about. So my take is the basic thing from 1998 still looks good, but there are some cracks. We have a lot of work to do, but we need to be really careful about doing blind analyses because humans are very good at getting, putting their thumbs on the scale, even if they don't intend to get the answer they want. And we're really getting into sociology here, where people seem to have what I can only say is emotional attachment to the values. I try to stay away from that as best I can. But there's a whole bunch else to do. We're not done. I won't go through these things, but just know it's not just measuring omega lambda and omega matter that matters. There's a whole bunch to do. And as indicated, if the universe keeps on accelerating, as it appears to do, time is limited. We only have about, a trillion years are left to be cosmologies. And in the future, all the galaxies we see today will disappear. And so we'll all need to be stellar astronomers rather than anything else. Thank you very much.
Thank you very much, Brian, for your very interesting and so amazing talk. Now we have a few minutes for questions from the audience. Tenemos unos minutitos para preguntas de la audiencia. ¿Queréis preguntar? Podéis preguntar en español y traduciremos, tanto John como yo intentaremos, John seguro lo hace bien, traducir la pregunta. Ánimo. Antonio.
Hi. Impressive presentation. Thank you very much. It's been quite enjoyable. My question is about the inflation. So it's dead forever, or what's your current view of this?
So, what is this? How do I turn it on?
Hello? Yeah.
So, no, inflation is alive. Inflation had a few things to do. It predicted that the universe should be flat. It's flat to 1 part in 1,000. That's pretty hard to, something had to make it that flat. So it seems to be right. The other thing it predicts is essentially what the quantum fluctuations, when they get expanded to very large size, have a very specific distribution of essentially size. And they more or less have gotten the details of that correct as measured in the cosmic microwave background. At first order, it's scale free, so that's not very exciting. But then they predict it curves off at the end, and they get more or less exactly what was seen. So everything it could do, it has done. Now, it still doesn't mean why we know that inflation occurred, but it would seem that something like it happened. And one thing I do hesitate is we talk about inflation. I think we need to be open to inflation being any number of things. It's a time when the universe was exponentially expanding. So to my mind, the question is, why did inflation stop? That's, I think, really a big question. And personally, to give you a sense of the type of things that could happen, is imagine the universe of all universes is exponentially expanding. This is going to be called internal inflation, if you've heard of it. The whole universe of all universes is inflating, and we are a little bit of that. That has, for whatever reason, the inflation has stopped. And so our universe is embedded in this super universe that goes on forever, and we are this little thing that, relative to the universe of all universes, that materializes. Now we know that exponential expansion of the universe of all universes probably has existed for all times and always will, and we end up being just like a champagne bubble in the middle of it all. That's our little bit. We kind of look quasi-infinite, flat. We have our own little bit. But you can imagine then there are an infinite number of these universes being created at all times, but we never are in contact with them. It's just our own little bit. So that's sort of the idea that most resonates with me. How do we test it? Not so easy, it turns out. But if that were true, we end up that anthropic argument that we can only live in a universe that we can observe, which kind of makes, as I said, it's not very instructive, but it's definitely got to be true. So you sort of live in a universe you can live in. Alpha, the fine structure constant, has to have a certain value, and also G has to have a certain value, or else it doesn't work. So I don't know. It's sort of metaphysics rather than physics, and not completely, does not make me happy.
Very anti-Copernican.
Well, I disagree. It's just you have to look further. So we live in our own special universe, but there's a universe of other universes that looks more or less, at that point everyone sees the same thing. But you do need to look beyond the horizon. And the problem is, we can't look beyond the horizon, even if it is there. So I still think it's Copernican. But we can have philosophy over lunch.
Hello, Mr. Brian. First of all, thank you for coming to our city and to our university. It's an honor having you here. I'm going to ask you something more normal. I'm not physicist, so it's
so
more,
I apologize to you. Yes.
No, it's okay. It was very interesting.
Yeah.
But I'm curious about this. So I would ask you, all of you, if you could, knowing automatically right now how everything started or how everything ends, what would you choose? The beginning of the end, or the end?
So, it's an interesting question. They're kind of morally equivalent for me. If you go before the Big Bang, that's the horizon I can't know about. If you go to the very end, I have to be omniscient. That is, I have to know everything that's going on in the universe to actually understand the end. Because if anything changes that I don't know about, then I don't know the end. So I'm going to be honest, I'd flip a coin. They're basically the same to me. If you could tell me the beginning, and you could answer everything I wanted to know about the beginning, that means I'm omniscient and then I can figure out the end. But you'd have to be able to answer every question. And I would need to ask you which questions to ask. That would be part of that.
Hello, thank you very much for the presentation. It was a pleasure to be here, enjoying. I wanted to ask, are these huge findings in the field of physics or astrophysics, or to what extent are some findings discovered by serendipity, by chance, or is it the normality that someone has a hypothesis that is going to be tested and it's actually, and this brings up important discovery?
So it's a mix. My experience is that small groups playing around and making serendipitous discoveries give most value in science. But to really understand them and then potentially to translate them, then you need to bring in the machinery. Right? So it kind of works hand in hand. Both have their place. But the little experiments where people are, messing around, and in the case, for example, my colleagues in Chile suddenly realize that there is a way to measure these distances way better than anyone has ever done before. Well, that was sort of by accident. They were trying to do something a little different. They came onto it, and then that allowed a much bigger team to use that to do the next thing, which by modern days was only 20 people, so that's a small team. Now the people who are trying to understand our result are teams of thousands. So I'm not part of those teams anymore. I look at it and going, I got better things to do with my life. I'm going to go back with my graduate student, do the little things, and hope I have some luck to find something new. So it's a balance. You need to have both. But it's really, really easy to forget about the little things. The individual researchers are an incredibly important part. And them having ideas, stumbling onto things, that is a super important part that we and especially governments forget about. Because you don't know what they're going to find. Yet they continually find things that are useful and power, keep the whole bit working.
So they should be funded. This kind of
It
high-risk idea?
It needs to be funded. It needs a certain fraction. You don't need to exponentially grow it. But as a reflection, one of the things I do is I am the chair of the Singaporean Academic Research Council. And I hand out all the grants in Singapore for this type of research, bottom-up individual researchers. The Singaporean government, which we think as being very, very practical, dedicates a fraction of the GDP of the country, which is higher than literally any other place. They give me instructions, which are 3 lines long, and say, fund the things that you think are most excellent, more or less, and then they let me go to it. That's all they do. So that's the way you need to do this. You need to fund excellence, but you don't want to then say, then you want to have other programs to make that basic program translate into washing machines and industrial policy and stuff. Keep them separate. Singapore does that. And they have built up, in a country of 5 million people, 2 of the strongest universities in the world in 20 years, spending less money than most countries do on research, just by not being stupid about it.
Perfecta extracción, desde luego. ¿Alguna pregunta más?
No such thing as a dumb question. There's really hard questions. I don't like those.
Bueno, pues si no... John, ¿tú alguna pregunta tienes?
No. Tengo preguntas. Aquí no.
Bien, pues yo quiero darle las gracias de nuevo a nuestro invitado, a Brian Schmidt, por estar aquí con nosotros. Dar las gracias a vosotros todos por la asistencia a esta conferencia. Creo que ha sido realmente interesante. También su respuesta a las cuestiones que hemos tenido, especialmente esta última, que nos enseña a todos el camino que deberíamos seguir para hacer ciencia, y a nivel de comunidad, a nivel de país. Y bueno, reitero mi agradecimiento a todos vosotros, y ahora que tenemos la agenda un pelín apretada, que tenemos que marcharnos a seguir con la planificación del día, pues de nuevo, muchísimas gracias. Brian, thank you very much again for being here with us, for your talk, for your answer to the questions, and for your encouraging example of how we live the science.
Right.
Thank you very much.
Thank you very much.